Right. Now we're going to look into the friction coefficient, as I said in the previous lecture. So the last things that the von Karman calculate using his momentum integral analysis was this friction coefficient. The friction coefficients are just like any other coefficient and typical that we use in the fluid mechanics, and then it was two two times the tau wall and divide by rho u naught squared, which is this is basically this rho u naught squared. This equations is actually basically the dynamics pressure, half of it, because this is actually the dynamic pressure is half rho u naught squared. This is half of the dynamic pressure, so we got the rho u naught squared as a denominators. And then we did use these equations, and then we substitute the value of the wall shear stress. This is the value of shear stress from that we got it from the control volume analysis that have been done before, and then we substitute here in these equations, and also is a quadratic velocity profile, as we look discuss in the previous lecture. All right, so now, and also now what we going to do is we got this coefficient of friction, which is equal to 4 mu u naught divided by delta rho u naught squared. So basically this one, if you look into this is actually the half of, this is or we call it the new, or we call it the kinematics viscosity. Now we're going to solve this equation. So let's I put it here. So VF, I revise these equations, and it's become the new one, which is the coefficient of frictions now equal to the 4 mu u. Sorry, this is not mu. This is nu, and then divide by delta u naught. So in this case, if we substitute the values of the from that we got from quadratic velocity profile just now in the previous lecture, so we can write this as a 4 mu divided by square root of 30, and then this is multiplied by nu divided by u naught x multiplied by u naught. Right, you can do some more simplifications here, and then this is what you got it after this. This is a square root of 16 over 30, and then we multiply by v nu over u naught x divided by the square root of nu divided by u naught x, and then we can write this as square root of 8 over 15 r e x power of minus of, or you can write like this. Okay, this is what we get, and then you can see this. You can see this is the properties that we use in the momentum integral analysis, and a very simple tools that we learned in this course. Okay, and then the only approximation that we had to make and going through in this analysis was the velocity profile itself. So because the velocity profile is approximate, and then for that we assume it to be a quadratic functions, and then it was a really and the only place where there is a approximation made. And we see that we all can see that it was a bit of approximation, but it wasn't too far off, but from the uh, exact value, and then enable for us to get the delta as how they grow and through the boundary layer thickness, uh, and friction coefficient, so we can get the delta over x and also n coefficients of frictions through the momentum integral equations. So in the next chapter, we're going to look in the applications of the Navier-Stokes equations to the boundary layer, some of the approximations, the boundary layers, and then which is set by the Brendel, and of and his student Blasius, and then we will compare this their result with von Karman, and then to see the difference between the Blasius and the von Karman.